Hello, everybody. Can you see my first slide? Okay. So yes, in this talk, we're going to talk in three sections, really. So it's quite a variety of things. First of all, about the sun, a description of the sun and the science motives for Solar Orbiter. And then in the second part, about the lab development, which is really about the instruments and the ones that we worked on at RAL. And then lastly, the flight itself, what I call the space adventure so far. So I'm just trying to see. Oh yeah. So the second slide, yes, this is the timeline. So you can see, if you can read the years here, this stretches over several decades. And these three areas, first of all, the science motives was really a couple of decades up to 2012. So around about 2000, the science team would have been getting together and proposing this mission, the solar scientists, looking as well at the technology that's needed, the technology development to make the mission possible. And then, so I'll first of all talk about that. And then the second stage really began in 2012, when we had what's written here as the implementation, or if you like, the starting to spend the money and design and build the hardware and make the mission happen, get ready, plan the spacecraft, the launch, and so on. So we then spent about 5 years developing our instrument. And in 2017, that went to the spacecraft, and I'll describe the work that was done on the spacecraft at Airbus in Stevenage, and then on to tests in Germany, on to launch campaign in Florida, and then Solar Orbiter has been in the news because it was launched this February. And then in the third part of the talk, I'll describe this, what's shown in the green here, the what's happened so far, and the science phase, which is going to be look forward to from 2022. So you can imagine the scientists that conceived this maybe 30 years ago will be pretty excited. Okay, so first of all, introduction, something about the sun and why we have this mission. So going back a few hundred years to the major discoveries about the sun, I think this was one major one. Isaac Newton discovered and described the nature of light, and in particular white light from the sun. He showed that it's made up of the colors of the rainbow. So white light is made of many colors, and he did a lot of work on understanding of light. So then if we look at this in more detail, this is the spectrum of the sun. This is the brightness versus wavelength. So you see it has a certain shape, and the visible colors sit in the middle here, and you've got the infrared that we can't see on the right-hand side and ultraviolet on the left. Now, later physicists showed that this shape is characteristic in thermal physics. It's characteristic of a temperature, that when a body is at a certain temperature, it emits certain wavelengths. And the temperature calculated from this tells us that the sun is about 6,000 Kelvin in temperature. So it's what we call white hot. And objects that are cooler would be shifted more towards the red. So for instance, red hot, like molten metal, is about 1,000 degrees Kelvin. And I wanted to include here this little lamp because in our testing of space instruments, we often have to use sun simulator lamps. We want to recreate the sun's light in the lab. And then we need a lamp with a filament, typically that is also at this temperature. So a very hot filament, maybe 3,000 Kelvin, to get a good solar type spectrum. Then looking in more detail at this spectrum, you see these little notches here, these little dips. They're known as lines. They're spectral lines, as you may know, and they're associated in the sun with electronic transition between energy levels in an atom. So this circular diagram is a picture of the atom, a concept of the atom with the nucleus at the center, and these black dots are electrons jumping down from one energy level to a lower one. And each time that happens, there's an emission of light at a very precise wavelength. So you get these characteristic lines, and each line for each atom is tells us about one particular transition. So this has been described as a kind of fingerprint for the sun, or a barcode, if you like. If we can read the position of these lines and we do some atomic physics here on Earth, we can work out what atoms are in the sun. So therefore what the sun's made of, which was great discoveries over the last 100 years or so, and also their temperatures, because these transitions of certain energies will only happen if the atoms are excited enough to a certain temperature and a certain energy. And also here we mentioned the flows. We can also work out the flow of gas from the sun, whether it's coming towards us, erupting from the sun, or going away from us, because these lines are shifted with the Doppler shift, if you know about the Doppler shift. So this wealth of information. And then more recently, in the far ultraviolet, so down here where you don't see there's any light, there is lots of these spectral lines down here, and in the ultraviolet and X-ray, and these represent the higher energies in the sun. So by looking at those, we can see deeper into the sun and look at more of the physics. But to do this, we need space instruments, because this far ultraviolet doesn't penetrate the atmosphere. And this is one of the reasons for many space instruments in the solar area. So to introduce Solar Orbiter, I wanted to try and tempt you with these couple of mysteries about the sun. And mystery number one I want to describe is the discovery of this 1,000,000-degree temperature of the corona. Now, the corona means the crown. And what we're looking at here is the image of the sun in a total eclipse. So the moon is obscuring the solar disk. And this fiery thing around the outside looks like a crown, so it's called a corona. And it's been studied for many, well, for several centuries at least. People would go and visit parts of the world where there would be an eclipse and take these pictures. And it was actually 1869 that, in studying these particular spectral lines and cataloging things like hydrogen and helium in the sun, they discovered this line in the green, this mystery line. It's 530 nanometer, which is green light. And nobody could understand where it came from. And it wasn't, as it says here, it wasn't until 1943 when somebody at Kyoto University worked it out theoretically and by studying atomic spectra on the ground. They worked out this is iron atoms, iron 14, which is highly ionized atoms of iron, and also that it must be at 1,000,000 degrees Kelvin. So they solved that long-standing mystery, which is great, but they came up with another mystery, because the question then is, how can, this is about 1,000 times hotter than the rest of the sun, so how can the outer layer be so hot? And it doesn't make sense, because if you have any thermal body that's emitting heat, it should be cooler as you get further outwards, not hotter. So that's the first mystery. And the second mystery is about the solar wind. And this is more recently, this chap called Eugene Parker, you may have heard of, a solar physicist who in 1957, he worked out or realized that the heat flowing from the sun, all this energy coming from the sun, and this effect of the tails of comets being always blown in the direction away from the sun, he realized that these must be the result of the same thing. It must be some kind of particles streaming out from the sun. And he called this the solar wind. And he calculated the speed back in 1957. It was 400 kilometers per second, which is about 1,000,000 miles per hour. So a little bit very fast and a little bit strange. And his paper on this was rejected twice, apparently. It was a bit of an odd result. But in this case, we didn't have to wait as long for the answer to this, because of course 1957 is just before the space race, and it was you may remember, you may know it was the Soviets who led the way into space early on. And in 1959, this spacecraft Luna 1 directly observes the solar wind and measures its strength, and it proves that Eugene Parker was correct. So this is I think a great bit of science. It's a good example of how it's the revolutionary ideas in science that maybe at first are rejected, that once they're proven by experiment become a powerful new idea. So I can't say too much more about solar physics. I'm not a solar scientist myself, but to summarize, I'd say that many years later and many space instruments, since 1959, of course, we have some idea now about both of these mysteries, the coronal heating and the solar wind. And it's now believed that they're both driven by small-scale micro-explosions on the sun, that the outer layer of the sun is very active, and you have these small explosions that are driving the energy that creates these two effects. But also the sun is very complex. Just to say, the text in red here, it's really the sun is in turmoil between heat and gravity. I think that you know, the sun was formed by the gas falling under gravity, and then you have the fusion starts in the sun's core, and you've got all this heat and energy trying to get out and inflate the sun. So it's kind of in turmoil, and you've got all these extra effects. You've got magnetic field on the sun, you've got this radiation trying to get out, the sun is rotating, and there's all this fluid dynamics. So you can see from these flares and phenomena on the surface of the sun, that it's really a world in turmoil. And that brings us to solar orbiter. So this is a rather poor photo from a magazine, but it shows you where a solar orbiter is going to go. It's going to go just closer than Mercury. And the idea, of course, is to get close to the sun, because talking about these micro explosions, one thing they've found is that the closer you look at the sun, the more and more detail you see more smaller scale phenomena, and these are the answer to the mysteries. So we're trying to get close to the sun. Also, solar orbiter will look at the north and south poles of the sun for the first time. So we've never seen over the poles, and we always get this kind of equatorial view of the sun, but because of the magnetic field, that's more interesting to look over the poles. And there are 10 science instruments of two types. First of all, ones that image the sun, type 1 we might say, and the second type are so-called in situ instruments, which measure things at the spacecraft. They measure things like particles or the solar wind or magnetic field. Now, you may have noticed this other probe, this NASA probe called the Parker probe, named after Eugene Parker, and it's really very close to the sun and looks like it's doing a much better job. But the catch here is that this is so close to the sun that they can't look directly at the sun, that they can't have any cameras or optical instruments looking at the sun because the sun is just too intense. And so what they do have is just these in situ instruments. They can only measure things at the spacecraft. Okay, so the aims of solar orbiter then, as I said, it's always advertised as studying the sun up close. It's also doing that to try and connect events that we see on the surface of the sun with things that subsequently arrive at the spacecraft. So in particular, any eruptions. If some explosive event happens on the sun, then the idea is from a particular point on the sun, we can relate that to what happens later on at the spacecraft and try and work out, put the two things together. This is a schematic of the sun and the solar wind coming past the Earth. This is the Earth here, and this magnetic shape is the Earth's magnetic field, which any plasma or solar storm, as it were, that comes towards the Earth, the plasma is actually directed, as you may know, it's directed around the Earth, deflected by the Earth's magnetic field, and the magnetic field protects the Earth and makes life possible. And so part of the application of the mission is to understand what we call this Sun-Earth connection, or if you like, space weather, the fact that eruptions on the sun change things near the Earth. So in particular, there's been communication satellites that have been disrupted by solar storms. There's been even power grids have gone down. And if you think about human space flight and, for example, traveling to Mars, we would travel outside this protective magnetic field. And so this space weather and looking at predicting the space weather or measuring it is important. So that's why we have solar orbiter. So the second part, I'll talk about the how now. Rather different topic. This is about the engineering and the instrument. So first of all, how do they get to the sun? So this is a nice ESA poster. So the launch from Earth was on 10th of February. And first of all, we're heading off to Venus. And we do what's a gravity assist maneuver around Venus. In fact, on these, if you can read these dates, we do about 6 or 7 of these. So the idea here is use the gravity of Venus to lose speed, because as the spacecraft leaves the Earth, it's traveling around the sun with similar velocity to Earth, but it wants to fall closer to the sun. And to lose or gain speed in space, it's much more efficient to use a gravity assist from the planet than it is to, say, try to carry enough rocket fuel with you to use a rocket. In fact, that would be impossible. So as we go past Venus, we will lose speed and turn more towards the sun. The other effect we do using the gravity assist is to gain momentum in the upwards direction. So otherwise we're stuck in the kind of plane of the solar system where most spacecraft reside. And to get and look over the poles of the sun, you have to get this, in this graph, a kind of upward momentum. So it does that. It will go over the coming years, it will go past Venus quite a few times, and it kind of winds its way into the solar system, into the inner solar system. And just on the other side of the sun there is where we get the closest approach. So then there's the engineering. This is another poster of the spacecraft. When it's at its closest to the sun, what this, the point this is trying to make is that the intensity of the sun there is 13 times what it is near Earth. And not just the heat intensity, but also the radiation. So radiation damage could be a big challenge. So they designed the spacecraft naturally with, as you may have seen, it sits behind this large heat shield, which always has to face the sun. And the instruments which want to look at the sun, they have to kind of peep through the heat shield. So they only have very small holes in the shield or small apertures, because as soon as you look at something, you're taking all this heat in. And these little apertures have little sliding doors on what you can just about see, perhaps the doors that can close to protect the instruments if things overheat. And this little diagram of a thermometer here, this is to say that this heat shield goes up to about 500 degrees centigrade. And this is way too hot for any of our instruments to survive. Electronics can't work at anything like this temperature. And this is, to make the point more dramatically, this is a calculation of the heat, the temperature distribution on the spacecraft. So you see here, this white area is the 500 degrees, is the heat shield. Most of the spacecraft, this box shown in blue behind, is at a nice low temperature. And so the heat shield is really doing its job well. There's a kind of a gap between the heat shield and the spacecraft to limit the conduction of heat. And at this much lower temperature is where our equipment can happily work. So the spacecraft totally relies on this heat shield technology. And in fact, I dare say that if it lost its pointing direction, as some spacecraft do, if it did turn and let the sun onto the main part of the spacecraft, there would be quite a lot of damage. So about the instrument that we designed and built at RAL, it's one of, as I said, one of 10 instruments. It's a UV optical instrument, and these all have a fancy acronym. It's called SPICE, which stands for the spectrometer for imaging of the coronal environment. So you can see from the first two words, it's an optical instrument, and it's looking for these effects in the corona that I described. So you can see here, this is the instrument in our lab. This is actually just before it was finally closed up. The lid isn't on at this point. You can see it's about 1 meter long. And if I try and show you where it is on the spacecraft, if you look in the lower right here, this is, you can see the spacecraft and the heat shield and these little apertures now. Our aperture is the one pointed to with this yellow arrow, which is meant to be the sun coming in. We're at the top, we're at the kind of upper left in the box, if you like. And so this is a cutaway or a cartoon of the instrument sitting in the spacecraft. So the sunlight comes in through this little door. It then crosses this gap from the hot side to the cooler side. It comes into our instrument. And it's the sun is imaged by a mirror onto a slit for the spectrometer, and then from the slit to a diffraction grating. And if you know about diffraction gratings, a little bit like a prism, it spreads the light over all the colors. And that's why on the detectors, which are at the back here, I've drawn a little rainbow. This is meant to be the spread of light over the colors. So that's how the instrument works. And one particularly neat feature is that the mirror is designed to only reflect the ultraviolet light that we want. And the visible and infrared light, which would otherwise heat us up, the mirror is designed to actually transmit that light. So the unwanted light goes through the mirror, and then it goes off another mirror at 45 degrees and upwards here. We call this the heat dump. And you can see in the spacecraft picture, it then comes back out of the spacecraft. So we kind of dump it overboard. And we think this is a pretty neat idea to this thermal problem that we, we don't want this thermal energy heating us up. So what do? We just send it back into space. Then this is the kind of meat on the instrument. This is a computer view, but if we had a photo, it would look very similar. And what you see now is all the mechanics, the way it was actually built and put together. These little walls, so I should say the sunlight beam now is coming in, is shown as red, and the ultraviolet beam is in purple. These little walls are baffles to control scattered light. And the point about this is that these instruments these science instruments are a collaboration. So you see all these different countries who've contributed. So each country has to put in the money to fund the very expensive instrument and the mission. And in return, they then get access for the scientists 10 years later to the data. And these are very complicated bits of equipment. So for space, of course, the materials have to be very special. There's a lot of microfabrication goes on in the electronics. So our detector, for example, is like a megapixel camera like you'd get on a phone, but it has to work in the far UV, so it's pretty special. There are special mechanisms and thermal design and so on. And the point about this is it all has to be proven well before the instrument can start, because once you start the program, you're spending a lot of money. It's very expensive to go into space. And so this all has to be ready. So you can imagine this is, if you're into engineering, this is a great place to work. It's a lot of challenges and a lot of ingenuity and problem solving. And then I should mention the box here, the electronics box is really the brains of the instrument. This will do the communicating with the spacecraft, operating the instrument and the mechanisms, collecting the images and sending them back to the spacecraft to come to ground. So something on these special features, then I mentioned the mirror, and we had to do this special test of the mirror. We had to, in a little vacuum chamber, we had to make the intense solar beam, shine it through the mirror as you see here, and check the ultraviolet reflection. Measure these wires here are measuring the temperature. We had to measure the heating of the mirror, and even the fact that it would distort, because nobody has put a mirror that's going with light going through it of 13 times as bright as the sun before. And that all had to be done quite early on. And then the other special thing I'd like to show you is what we call the deflector shield. So this is a schematic here. This is to show you, again, the light path coming in would be the red arrow, and it comes into, this is part of the box, it comes in and is heading to the mirror at the back of the instrument. But as well as the light, we get these solar protons. So these are some of the particles of the solar wind that I mentioned. And if these come straight in and go onto the mirror, they will, over the time of the mission, they will erode the mirror and destroy it. And so we need a defense against this. And what we have is some high voltage plates. And because the protons are charged particles, they are deflected by these plates. And this is a simulation where it shows how they're bent in theory, and they actually harmlessly hit the side of the box rather than reaching the mirror. And I just thought this was really cool to show, because when I was a youngster, I think it was on Star Trek, they would have deflector shields as defense against the high energy beam from another spacecraft, and here we are using it for the sun. So that's probably enough about the instrument, just to say that it took us about 5 years to design and build it, design, build and test. This is the proud day, as you can see, when it's in the box and we're shipping it off to Stevenage, to the spacecraft, which is built by Airbus in Stevenage. This is a slightly dark photo, I'm afraid, but this is the large clean room at Airbus. This person here is crouched on a balcony where the spacecraft is, because at this point we're lifting the instrument on, this frame is on a crane. This is the instrument in the middle. It's been lifted off the bench and on its way to be put on the spacecraft. And you can imagine that was quite a exciting and stressful day for us to see it go onto the spacecraft. And then this photo shows it nice, neatly in place. As I said, it sits in a kind of corner of the inside of the spacecraft. We're looking at the part-built spacecraft here. And there it is, sat safely on the spacecraft. The other two things kind of wrapped in bags or foil here, these are two other instruments that are already on there. And the other point about this, you can see how intricate this is. There's a lot of wiring and piping that's got to be installed and all connected up. And you can imagine this person working in the spacecraft will have to work very carefully and methodically to get all this right. So then it was another couple of years before the spacecraft was complete. The spacecraft occupied, you can imagine, quite a large lab and lots of equipment coming from different people, including the 10 instruments, but it eventually is all kind of buttoned up and ready to go, and it's on this nice stand. And you can see the heat shield there at the front. This ring that it's mounted on is the ring that attaches it to the top of the rocket, of course, which is finally released once it's in space. So that, again, must have been a big milestone for Airbus. Then it traveled to Munich, near Munich, for the space test. So what you're looking at here with these people is this very large vacuum chamber, a space test chamber. And of course, this is to do tests, to test everything as much as we can as it will be in space. So inside the vacuum chamber, there are thermal panels here to heat or cool the spacecraft. They also had to use a very special large solar lamp to try to get close to this high solar intensity. And again, you can imagine a lot of complexity of hooking things up to get ready for this test, and how important these tests would be to get right. Because at each stage, everything has to be checked as ready, because there's a lot of money involved, of course, and it all has to be well assured. And so there was finally what we call the acceptance review in November, which to say that it's ready for launch. And at that point, it was sent over to Florida. So here it is in the clean room in Florida, November last year. And this is an even bigger clean room. And what you see here, what looks like banks of speakers, this is actually clean air flow, which is being directed over the spacecraft. So there's a kind of wind of filtered air here to keep the spacecraft clean during this stage. And then once it was ready, this is it being put into the nose cone of the rocket. You see here the so-called fairing, and it occupies actually just the lower half of the nose cone, and the ring that mounts it is at the bottom here. And this again must have been the big occasion when this is finally closed up and people had to take a deep breath and say, we're going to say goodbye to it now, it's all ready. Okay, then the third part of the talk is about the journey, what I call the journey so far. So as I've said, it was launched on the 10th of February. And what we're looking at here is part of the NASA live video footage that they show for launches. So you may, if you're interested in space, you may have seen the recent astronaut launch to the space station on the Dragon capsule. And this is the same kind of thing where they show a video. At this point in the launch process, it's the top left here, it says it's 45 minutes in and it's kind of over the ocean. And what you're looking at is obviously an animation because it's already in space. And you see the spacecraft there on the front of the rocket. And what it did was, I think was quite interesting. It launched from Florida and it did more or less half an orbit, which is why it's 45 minutes. And it had to keep this rocket on there. Normally the launch process is only a few minutes, but we had to wait 45 minutes halfway around the Earth with this rocket still attached to do what's called the escape burn. And this is where it ramps up and accelerates to leave the Earth. It escapes from the Earth and goes off into deep space at a heck of a speed. And the other interesting thing I learned about this was this launcher handover. So just after this point, I remember on the video, the people from the launch company, they start shaking hands because they've succeeded and their job is done. And what they've actually done is they've said, they've put the spacecraft in the sky almost and said to ESA, well, there it is. We put it where you wanted it and now you have to find it. And then ESA have to contact it, communicate with it and wake it up. And it just struck me as a very tricky moment, that the fact that, you know, somebody puts it in space and somebody else has to then find it. So that was quite interesting. So then the journey, this is a kind of map of the solar system, the sun and the Earth. So the Earth is over here on the left and the sun in the middle, and it's in the frame of reference as if the line from the Earth to the sun is fixed, which of course it actually isn't. But over the last few months, it's been heading off towards Venus. And these points here, the red, black, and the blue are the points where we did tests of our instrument. So we had first light in April. This is where we got the first images back, which was a big occasion for us. And then from those images, we devised some extra calibration tests, which we did. And then the third one, the co-alignment, is where we test with several instruments together. And it's going to arrive, it's going to do the Venus flyby around about Boxing Day. And then just to show you some measurements, this is how it's been getting warmer. So this is one of the temperatures on our instrument over this time period. And you see this gradual increase in temperature. And you see these jumps here when we were doing our tests. These jumps are because this is when we open the door on the instrument. And when we open the door and let the sunlight in, there's an increase in temperature. And then after our test, we close again and the temperature goes back down. So you can see we're getting warmer. And of course, as it goes closer to the sun, it will get warmer still. Then I want to make a slide about something else I learned that was interesting, what I call messaging for operations, or how you communicate with things in deep space. So they have ESA have a special deep space antenna that's in Argentina, and it's a very large dish and can send messages a long way to the spacecraft. And the spacecraft has a much smaller antenna so it can reply. But there's several, as you can imagine, several problems in sending these messages. When the spacecraft gets very far away, it takes up to 40 minutes for light to travel between the two, so you don't get an instant response. And also, because of the Earth's rotation, the spacecraft is only visible once per day for a few hours, maybe 4 hours per day. And this is called the ground pass. And that's because if you think about it from the point of view of someone at the dish on the ground, the spacecraft appears to kind of rise on one side of the sky and go across the sky in that time. So to do what we call the operations, to operate the instrument, we have to work around this. And what ESA did was they wanted to do these near-Earth tests as quickly as possible in the past 3 months. And that's because while we're near the Earth, we get much better return of the data. It's much easier to get the lots of data back. They had to do there were 10 instrument teams, so we had to take turns. They invited us to the control room for a few days each. So you go for a few days, and on the first day, we'd send our first commands, and maybe the instrument would go and do those tests, but we wouldn't get the data back within that 4-hour session. We'd get it back the next day. And that was all pretty exciting. And then, of course, we had the COVID-19 pandemic broke out, and this ESA control room is in Germany, and we couldn't travel anymore. So our guys then we had to do everything remotely, so even more challenging. So it was in July that ESA released the first images from Solar Orbiter, and it was a little bit frustrating because we'd had our first images for a good while, but I think they were right. They wanted to show all 10 instruments together because they wanted to make the point that these instruments are working together to solve these mysteries on the sun. And so they made quite a big press release with results from all of the instruments. And the little graphic they used for SPICE is this one here. So this is the solar disk that's measured by another instrument called EUI. And the SPICE instrument, we could take a zoomed in part of certain parts of the sun. And this is in the far ultraviolet. So we're looking at these more active regions of the sun. And in each part of our image, we're taking the spectrum, as I said. So to get these nice spectra of what the sun is emitting in the different atoms is really nice to see these results and how good the instrument is. And I should mention that the scientists have chosen these spectral lines to represent a range of temperatures. As I said, different atoms and ions give different temperatures, and we range from 30,000 Kelvin up to 1,000,000 Kelvin to study the sun in detail. And then I wanted to relate this, if I can, back to how the instrument works. So I said earlier on that the instrument produces this kind of rainbow. If it was invisible light, it'd be a rainbow across the detector. What you would actually see if you looked at the detector is recording this spectrum, so these particular lines, and the sun is imaged onto a slit in the instrument. And so we're actually at any given time, we're only looking at one slice of the image of the sun, but that slice is then being spread over all these wavelengths. So the diffraction grating, which acts like a prism, is spreading the light over all these wavelengths. So then the question is, how do we get the two-dimensional image? So what we have to do is we have to take this one-dimensional slice of the image that we get at a particular time, and we use a mechanism and we scan it across the sun east to west and slowly build up the 2D image. Then I can just got time to show you one more thing about the calibration, which was quite dear to me. So the Solar Orbiter spacecraft can look at different points on the sun. It can direct itself if something interesting is happening. But during calibration, we asked it, or the instruments asked it, to go and look at the north pole of the sun, the south pole of the sun, and the east and west limbs of the sun. And this is because then you'll get, if you look at the edge of the sun, you get a sharp feature and you can basically tell where you're pointing. And the idea here was to check the alignment of all the instruments. Now for us, how well are we aligned to each other and on the spacecraft? For us, we hadn't been able to look at any pictures from the instrument in the UV ever since we had it at RAL. So for 4 years, we haven't been able to do any checks. And so in all the time it went to the spacecraft and was put on the spacecraft, and all the assembly of the spacecraft and the tests that were done, we would be maybe quite interested to know, is it well aligned? Okay, and these are the results. So these are the north and south poles and east and west of the sun. And if the alignment was perfect, these edges of the sun would appear exactly in the middle of the images. So they'd be exactly in the middle of the black rectangle. And so you can see it's a little bit out. It's not too bad north-south, but east-west, it's off to the side a bit. But as you can imagine, we were very pleased about this. This was a great relief that all this work that had been done by several teams of people was all fine. So to summarize then, yes, in the first part of the talk, we described how people make these missions happen, how the scientists have to get together, and also the technology, and then the process of this development and engineering of the instrument and the spacecraft and the launch. And then we're now in this cruise phase, which means it's on the way to the sun. It takes a while, as I said, to wind its way to the sun. But we've done these first tests in the first few months, and it's great news because all the 10 instruments are all working beautifully. And there isn't much around about the science yet, but I'm sure that when it gets close to the sun from 2022 onwards, you'll hear more, and there'll be more about the discoveries of how the sun works. And then finally, acknowledgements. I mentioned before, this is really big science. To do things on this scale, you need international collaboration, lots of organizations, and these are all the organizations that were involved just in building this one small box, just in our instrument. Okay, so thank you for listening. I think I'm done.
Thank you very much, Martin. That's brilliant. We've just got a few questions in at the moment. If anybody else has any questions, please do type them in the Q&A box at the bottom and we'll ask them to Martin. First question, how far will Solar Orbiter be from the Sun at its closest approach?
I'm not sure in miles, but it's almost 1/4 of the Earth-Sun distance. So the Earth-Sun distance is called an astronomical unit. So it's a 1/4 of an astronomical unit. So if you like, 4 times closer to the Sun than the Earth is, which is just a bit closer than Mercury.
Okay, that's fab. Does the orbiter always keep the heat shield facing the Sun naturally? And if the orientation got changed, does the orbiter have any capability to reorient itself?
Yes, it doesn't naturally face the Sun. It has to be steered with thrusters and momentum wheels. So it has to be actively pointed at the Sun, and spacecraft use basically a guidance system. They use things like a star tracker to take a fix on where they are and keep pointing. And it would definitely be a problem if something failed and it lost the pointing. Then things could overheat quite quickly. I didn't catch, was there a third part of the question?
No, just the second part of it.
Okay.
They have the capability to reorient itself. Does the solar orbiter have any degree of autonomy? Given the 14-minute delay, if one instrument sees something interesting, can it bring the other instruments into image the interesting area?
Well, yes, it has. It does have. You're right. It does have to have a lot of autonomy. In fact, when it's at the closest approach to the Sun for a period of about 10 days, there's a kind of observing plan which is done automatically, because when it's close to the Sun, we can't communicate with it because the antenna basically doesn't work. The Sun is too bright, even in the radio waves. So it works autonomously at that point. And yes, there is a mechanism for some instruments to raise a kind of idea to say it's something over there is interesting. Let's go and look at that. But I think it's not possible. Most of the steering is done by moving the spacecraft, and it's not possible to do that autonomously. So I think what actually happens is, just before in the lead up to the observing cycle, the scientists will look at images and identify objects of interest, and then ask in advance for the spacecraft to go and look at an object. And in fact, during the 10 days of collecting the data, the Sun is rotated. When you're close to the Sun, the Sun's rotation has a big effect as well. So the spacecraft, I think it does track things across the Sun. But otherwise, it's not autonomous. It has to be done in what's called the near-term planning by the scientists. But you're right that any interesting eruption, that's exactly what the spacecraft wants to go and look at. Yeah.
Lovely, thank you. What kind of mirror was used on the solar orbiter to capture the images?
So this special mirror that I mentioned is a thin layer of something called boron carbide, a new material, and it has to be very thin. It's so thin that for visible and infrared light, it passes through the mirror because it's a very thin layer on the glass. But the ultraviolet, which has shorter wavelength, is reflected by this layer, and it's because it also has to be radiation resistant, and it's because it's so thin that it has this problem of getting eroded by the solar wind that I mentioned.
Okay. Is the spacecraft in any danger from coronal mass ejections?
Well, that's a good question. I'm not sure, but it is in danger from, in general, from radiation. So the radiation testing on all spacecraft is a bit of a tricky issue, because people want the spacecraft to be guaranteed to last a certain time. And I think because it's close to the Sun, there's some unknowns about the radiation. And yes, when you get a coronal mass ejection for all spacecraft, you can get a kind of jump in the damage, because although the electronics, for example, is supposed to gradually degrade over 5 or 10 years, when there's a big event, you know, on other spacecraft, you see a kind of jump in the damage level. So I think it's, yes, it is a possibility. I think especially later in the mission, when radiation damage comes into play, people will start to worry about how long it's going to last. I think I would say it's perhaps not guaranteed to last. It's designed for 5 years, but I think, yes, it does depend on what kind of hits it from the sun.
Okay. Could the instruments be used to look at conditions on Venus as it flies by?
Yes, I think they could do. Some of the instruments are invisible light, although a lot of them are ultraviolet light, where Venus might not be so interesting. I know that in our case, I believe the spacecraft isn't pointing at Venus during the flyby because of the way it's traveling. So maybe it just wasn't planned to study Venus. But related to that, the spacecraft has been studying some stars, although it's pointing at the sun, where there's a star appearing close by the sun, it's been able to observe that and use that for calibration. Yeah, and also I think it's observed a comet. It was fortunate that it encountered a comet recently and did some observations of that. Was
that comet Neowise?
I'm not sure if it was the one. No, I don't think it was the one that we've seen recently.
Okay.
I'm not sure. But when I say encountered it, it was kind of flying near the comet's tail and so on.
Oh wow, that's fabulous. That's answered all of our questions, unless anybody has any last questions they want to get in. So thank you very much, Martin. That was absolutely fantastic, and absolutely loved hearing all about it and the Rutherford Appleton Laboratory's involvement. Thank you very much, everybody, for joining us, and we will see you next time.